So for this video, I want to start by looking at part 1 of the rotational collisions lab that you did. So in this part 1, there was a large spinning disc, this big wood one, and they dropped this black disc on there. Now, as soon as that black disc hits, the large spinning disc slows down. And you were asked two main questions. First, what happens to the rotational inertia of this system after the collision? Now, rotational inertia depends on both mass and the way that mass is distributed. When you add this second disc by dropping it on there, you're significantly increasing the mass of your system, which increases the rotational inertia. And that's the moment where everything slows down, so the system loses angular velocity. So what I'm getting at is that there's something important that involves rotational inertia and involves angular velocity. So if I go to the formula sheet, towards the lower left, there's this equation right here, where we have rotational inertia, the capital I, times omega, which represents angular velocity. And they use this variable L and set it equal to that. L is going to represent angular momentum. And it makes some sense that this could be what's staying constant. Because if L is going to stay constant, when you increase one of these quantities, the other has to decrease to compensate. So when they increased the rotational inertia by dropping that second disc on there, the angular velocity decreased, which kept the angular momentum constant. Now, this has really strong parallels to what we did with momentum earlier this year. So we had that momentum, which is a P, is mass times velocity, where mass tells us about resistance to changes in motion. Now we have rotational inertia times angular velocity, where rotational inertia tells us specifically about resistance to changes in angular motion. And so these two quantities are really similar to each other, and the things that you learned about momentum transfer earlier this year are still going to apply. And so we can use a lot of those same tools. So for example, I'm going to do an SOS diagram to go through what must have been happening in that part 1 of the lab. So the SOS diagram, that's where you have a sketch, then an interaction diagram, and then a second sketch that shows the final situation. I'm going to start with my interaction diagram, where I'm going to just identify what interactions are happening and define my system. I've got a big disc and I've got a small disc. The big one is that wooden one that was spinning at the very beginning, and then the small one is the black one that was just dropped on there. Now, when that small one is dropped, there's going to be both a normal force and a force of friction acting on these. There is also an interaction with the earth. There we go. So we have a force of gravity interaction with each of these. Now, for this normal force between the small disc and the big one, once that small disc lands on top of the larger one, these two balance each other. All right, and then we also have the stand that that big disk is sitting on. And I'm going to call that a normal interaction as well. And then that normal force equals the force of gravity. Now for my system, I'm going to go ahead and put both disks in my system at this point. So now the only external interactions I have are balanced. And so that means that there are no unbalanced forces on my system. Now, that force of friction between the big disk and the small one isn't balanced by anything, but because it's internal to my system, I get to ignore it. So then if I do my initial sketch, I've got my big disk. Not a real pretty drawing there, but that's all right. I'm going to do a little I with a subscript B to indicate that big disk's rotational inertia. And then I'm going to do this to indicate the initial velocity. And then I've got my smaller disk. This is the black one that they dropped on there. Initially, that smaller disk is not rotating. So I have omega naught for the small disk equals 0. So if I were to find the total angular momentum of my system before, that really just equals the rotational inertia of the big disk times the initial velocity. Now, if I do my final sketch, and as you can see from the quality of my drawings, I will definitely not judge anyone else's artwork. Now it's got some final angular velocity. If I think about just the big disk, its rotational inertia on its own hasn't changed. But now I've got this little disk rotating with it. And they're rotating with the same angular velocity. So I'm just going to call them both omega f. Whereas like over here, I might call it omega naught small and omega naught big, just to make it clear that these are different quantities. And so then, if I was going to find the total final angular momentum, I could do the angular momentum of the big disk, which is its rotational inertia, plus the times the angular velocity, and then I'll do plus the angular momentum of the smaller disk. And then, because there's no unbalanced interactions, I can set all of these equal to each other. So the total momentum that I start with has to equal the total momentum that I end with. Just like we had earlier this year when there's no unbalanced forces, total linear momentum you start with is the total linear momentum you end with. Now, one interesting thing with rotation is you don't necessarily need two objects for this to come into play. In this case, we had two separate disks, and by colliding them together, we were able to change the angular velocity. But if you have some object that's able to change shape while it's rotating, a real classic example is if you have a chair that can spin, and if you hold something fairly heavy in your hands, so for example, if you have a few books or something, get the chair spinning, start with your arms out to the side, with those heavy things in either hand. Get spinning and then pull the books in, and you should notice yourself speeding up. This is also something you see on display a lot in figure skating, when a figure skater wants to change the speed that they're spinning at. They'll extend their leg or extend their arms and slow down. They'll pull their limbs back in to speed up. And so changing the distribution of mass, even if you don't have another object coming into play, does change your velocity through that conservation of angular momentum.